Welcome to this web note on the topological structure and properties of metric spaces. Um, we are not going to be exhaustive in terms of the details of the topology defined in metric spaces, but we will be only looking at some of the properties, fundamental properties of the topology of metric spaces, the natural topology, or also known as the strong topology. First of all, what will inspire us when we're dealing with the topology of metric spaces is to look at the real line. So really, we will look at the real line, and the idea behind the analogy between the real line R and the metric spaces is to, whenever we have, because we know that if x and y are in R, x and y are in R, the distance between x and y is just the absolute value of x minus y. So inspired with this, we'll take exactly, for example, if we look at MD, a metric space, okay, throughout this web node, MD will stand for a metric space. So if I don't write D, that is understood as being the distance on the metric space M. So in this case, we will say, for example, the analogy with the closed and open intervals centered at x with radius epsilon becomes the two new objects, okay, x epsilon, which is the set of y's in M, such that the distance from x to y is less than epsilon, and BC of x epsilon equal y in M, such that the distance from x to y is less or equal than epsilon. So the first one is the analog to the open interval, while the second one is the analog to the closed interval. X would stand for the center, and epsilon stands for the radius. And the reason why we call them center and radius, and these two sets B's are balls, because in the case of R2, okay, in fact they are just the disk, the open disk and the closed disk, and in the case of R3, they are exactly the open ball and the closed ball, the sphere. And that's why in metric spaces we borrowed the terminology of open and closed ball. So these are known, so B0 is the open ball, okay, and BC is the closed ball. X being the center and epsilon being what? The radius. Excellent. Now, in order for us to define the concept of open sets, okay, because remember that a topology, in order to define the topology, we need to define the concept of open sets. So open sets, and in order to define open sets, we need the concept of interior points. So let n be a subset of M. We say that A is an interior point of N if and only if there exists epsilon positive such that the open ball centered in A with radius epsilon is in N. So in particular, an interior point belongs to the subset. Okay, so you don't have only the point; you have a ball, an open ball around it inside the set. That's what we call an interior point. So the definition of open set, now we're ready to give a definition. N is said to be open if and only if any point in N is an interior point of N. So once we have the definition of what is an open set, it's very easy to check that. As an example, of course, we have the empty set, the entire set, and the open balls are all open. Though the definition for empty set and M is easy to prove or to check that they are open, for the open ball it needs a little bit work, but it's exactly the same proof, similar proof using the triangle inequality of the distance, etc., etc. It's very easy to show that in fact any open ball is in fact open, and this is why we call open balls open. Okay. Also, it's very easy to check that any union of open sets is open, and any finite intersection of uh, of open sets is open. Uh, Once we have defined open set, it is clear that the next is to define the concept of closed sets. And this is a little bit easier. It's enough to say, okay, a subset N of M is closed if and only if its complement is open. So here, as an example, it's very easy to check that the empty set, the entire set, and closed balls are closed. Moreover, any intersection of closed set is closed, and any finite union of closed set is closed. Okay. Once armed with this, okay, then we can define, as we did in the real line, as well as in any abstract topological space, we can define the concept of interior and closure. So a point, so we take a set A, let A be a subset of N. So the interior of A is the union of all open subset such that O is in A. And again, this union is not done on a finite, on an empty family, because the empty set is open and this is a subset of A. So it does make sense, this definition. So it's the biggest open set inside the set A. It's always a subset of A. And it is the biggest one, and keep in mind that the union of open set is open, therefore the interior of A is an open. And the closure of A is the intersection of closed subsets such that A is a subset of C, and this of course is bigger than A. So the closure, since it is an intersection of all the closed set, it is a closed set, and since all of them do contain A, then the closure contains A, as well as this family is well defined because M is one of them. It is closed and it contains A. Okay. once we have done this, we can now define some other properties of closed and open sets and vice versa. But instead, what we are gonna do, we are gonna try to investigate. This is what we are trying to do in this web note. Investigate the main problem here, which uh, uh, is there some special property satisfied by this topology in metric spaces. So in other words, what is special about this topology? And in order, in metric spaces, okay, so in order to understand this, let us first investigate the concept of uh, uh, interior point versus the complement, and what is going to lead to, as we did on the real line. So here, let us go back. So here, let n be a subset of M, okay, and let A be an interior point of the complement. Okay, then in this case, we know that there exists epsilon positive such that the open ball is inside the complement, or that the open ball intersect n is empty. Okay, so looking at this, we can ask now, what happened if we have now points? So now similarly, let A belongs to M such that for every epsilon, the ball intersects N is non-empty. Obviously, if A belongs to N, then this intersection is not empty. Okay? So here, to take out this trivial case, we assume that this intersection has a point other than A. So here, what happened if we take let A belongs to M such that for every epsilon, okay, the open ball intersect not N, but N minus A is not empty. In other words, that this intersection has a point other than A. And some of the properties of this concept, if such point exists, first of all, let us give it a name. So such point will be called an accumulation point of N. Okay, so it's not very hard to check that if N has an accumulation point, then N must be infinite. And there are sets in metric spaces which are nice and they don't have any accumulation points, non-empty and they don't have accumulation points, and even infinite and they don't have accumulation points. So it is clear that we have the following property. It's not very hard to prove. Theorem. N subset of M is closed if and only if N contains all its accumulation points. So in particular, if it doesn't have accumulation point, then the set is what? Is closed. And this can be a little bit improved. We don't see it here, but the next result will clarify this point a little bit more, that if A is an accumulation point of n, then there exists xn in n such that the limit of the distance from xn to A is equal to 0, okay, and xn are all different from A. It's enough to go back to the definition of accumulation point, and let this epsilon, because we said that this is for every epsilon, and here in this definition here, we took for every epsilon, and we can let epsilon go to 0, like 1 over n, and this is how we come up with this xn's here. This, of course, in fact, I forgot to mention that this property, if you have such sequence xn, then in fact A is an accumulation point. So it's not just if you have an accumulation point, then you have this property. It's if and only if. So the converse is also true. The converse is true. Let me just recall something here, that if xn is a sequence in M such that limit of the distance of xn to some point A is equal to 0, then we will say that xn is convergent and its limit is A. Okay? We will write limit of xn when n goes to infinity equals to A. So again, what happened is that it becomes a little bit easier, that a set is closed according to the previous theorem, is closed if and only if the limit accumulation points belongs to the set, and accumulation points are limit of a sequence generated from the set. So this gives us some kind of sequential characterization of closed set. And to be a little bit more precise, we can come up with a new concept once we drop this property here. Okay, if we drop this one, then we can come up with a new concept called the concept of limit point. So here, limit point. Okay, so A is called a limit point of n if and only if there exists xn in n such that limit of xn is equal to A. So of course here the concept of limit point for a subset n is different from accumulation point, in the sense that here we don't assume that the xn's are different from the limit. Okay, so it's very easy to see now, corollary from the previous theorem, that n is closed if and only if n contains its limit points. Okay, and not only that, one can also prove the following, that the closure of n is the set of limit points of of n, which is equal to n union the set of accumulation points of n. So this is good because it gives us a nice characterization of the closure of being closed using the concept of accumulation points and limit point. And both of them can be defined by using sequential. So there is some kind of inherent or something deeper here, in the sense that in metric spaces, countable behavior somehow lead to something very, very nice and defines a concept. That's not the case. That is not the case for general topology. You cannot have a sequential characterization of closed sets in general topological spaces. Next, okay, we can use this to prove the following nice result. Just I will call it a little exercise. And in order to define this, let us define the distance between points and sets. Okay, so let A be a point in M and N a subset of M. We define the distance from A to the set to be the infimum of the distance from A to X, where X belongs to N. Okay, so now we have the following property. The distance from A to N is equal to 0 if and only if A belongs to the closure. And in fact, what we can prove is that the distance from A to N is equal to 0 if and only if A is a limit point of N. Next, we can define another exercise. We can define the concept of diameter of a set. So let's take n subset of M. Okay, we'll say that n is bounded if and only if the quantity dn equal supremum of the distance from x to y, x and y in n is finite. So this quantity d n is called the diameter of n. Another notation is given by, which students may find in the literature, delta of n. Okay, it's easy to check that we have d of n equal d of the closure of n. So here, keep in mind, it's easy to see that if A is a subset of B, then the diameter of A is less than the diameter of B. So we know it's clear then that the diameter of the closure of n is bigger than the diameter of n. But what's nice is using the properties of the distance with respect to the limit of sequences, it is also true that the diameter of n, the closure of n, is less or equal than the diameter of n, which implies that they have both the same diameter. So this will be useful in a result later on when we look at some other example. Next, we defined a concept that is related to the convergence of a sequence. And let us start first by doing a little investigation. Let xn be a convergent sequence in M. Set limit of xn equal to z. Then we know for any epsilon, there exists an integer such that for any n greater than n0, the distance of xn to z is less than epsilon. That's the definition of, coming from the definition of convergent sequence. Now, using the triangle inequality, we can prove that for any n and m greater than n0, the distance from xn to xm using the triangle inequality is going to be less than 2 epsilon. Okay? So if a sequence is convergent, it satisfies this property, the following property known as the Cauchy property. Cauchy property. Okay? Xn is said to be Cauchy if and only if for any epsilon there exists n0 such that for any n and m greater than n0, the distance between xn and xm is less than epsilon. And what's interesting is that a sequence which is convergent is Cauchy. Okay? And what would be interesting here to have is whether the converse is true, that a Cauchy sequence is convergent. And what does it make us gain? What is the gain by using this Cauchy behavior instead of convergent sequence? In the definition of Cauchy convergent sequence, we do have a limit. We know the limit. We say the sequence xn converges to x, for example. So we know the limit. In the case of Cauchy, is a property satisfied by the sequence. We don't talk about the limit. We have no clue what the limit is. And therefore, this Cauchy behavior is a good behavior to have if we are able to imply convergence from the Cauchy. So this is happening if the space is what's called complete. So we have a new definition. M is complete if and only if any Cauchy sequence in M is convergent to a point in M. So in a complete metric space, convergence and Cauchy behavior are equivalent. And this is really interesting because it does not force us to consider the limit. It's enough to just check on the sequence itself and show that the sequence is Cauchy. Okay, so we know in this case that we have a limit. Not any metric space is complete, because if you take the set of rational numbers, it is a metric space for the absolute value, and we know that it's not complete because we can find a rational sequence which converges to square root of 2, which is not a rational number. And therefore, that rational sequence will be Cauchy, but will not be convergent because the limit is not a rational number. Complete matrix spaces enjoy some very nice properties, and one of them, first of all, is to before we go into some deep properties, we need to make just a remark. Let me make a remark here that Cauchy or complete is proper to a distance. In other words, if we have two distances, okay, if D and D star are two distances defined in M, then we do not have, in general, we do not have MD complete if and only if MD star complete. And the reason is because Cauchy sequences for one distance may not be Cauchy sequences for the other one. Except in one case, very interesting case, okay, except if D and D star are equivalent. This is a new concept, and what it says, what does it mean to be equivalent? Meaning that there exists alpha positive and beta positive such that alpha distance of x to y less than distance d star of x to y less than beta times the distance of x and y. So for any x and y in M. Okay? So if that's the case, if the two distances are equivalent, then Cauchy sequences for one are identical to Cauchy sequences for the other one, and therefore one is complete if and only if the other one is complete. The next property, okay, as we said, is proper to complete metric spaces. It's a beautiful theorem. Okay, so M is complete if and only if for any sequence of closed non-empty subsets in M such that they are decreasing, they are getting smaller and smaller, and limit of the diameter is equal to 0. So for any such sequence, we have the intersection of the CNs is not empty. In fact, it's easy to see that the diameter of this intersection is equal to 0 because it's more than all the CNs, and therefore if it is not empty, it must be reduced to 1 point. So the interesting part is not to be reduced to 1 point, is to be non-empty. Okay? This property fails if we drop the case that the limit of the diameter is equal to 0, for example, because we can take, in example, we can take in R, and we can take Cn to be n plus infinity. So the condition so these closed sets are decreasing, okay, they are becoming smaller and smaller, but the intersection of the CNs is empty. So the condition on the diameters is very important. And this, by the way, property characterizes completeness. So the idea of the proof, just for the sake of idea of the proof, I'm not going to go over the details of the proof, but the idea of the proof, okay, number one, we assume that M is complete. Let Cn as described above in the theorem. Because they are not empty, xn belongs to Cn. Then it is easy to check. It is easy to check that this sequence xn is Cauchy. Since M is complete, then limit of xn when n goes to infinity equals to z exists in M. Okay? And then this z belongs to Cn for any n, and this of course will imply the intersection of the Cn's is not empty. Now, conversely, we want to assume that for any decreasing sequence of closed sets, the intersection is not empty, provided that the limit of their diameters is equal to 0, and prove that M is complete. And for that, let xn be Cauchy. Okay, we need to prove that xn is convergent. For this, set Cn to be xn plus 1, etc. Okay? Now, we have, it's very easy to see that d of Cn exist. In other words, they are bounded, and limit of d of Cn is equal to 0 when n goes to infinity. This is because the sequence is Cauchy. Once we have done that, then note also that Cn plus 1 is a subset of Cn. Okay? So the sequence of the closure of Sn, okay, satisfies, this sequence satisfies all the properties of the theorem. So the intersection of the Cn bars is not empty, and any point z in this intersection is in fact the limit, is in fact the limit of xn. So your sequence xn is convergent. The last main result is a beautiful property due to Baire. Baire category theorem. So we will not look into this from a set theoretical point of view. We will give just the simplest form of the Baire theorem in metric spaces, because it will be very, very useful when we go to Banach spaces and normal linear vector spaces. First, before we state the theorem, let n be a subset of M. We will say that n is dense if and only if for any x in M, for any epsilon positive, the open ball intersect n is not empty. So in particular, a dense subset of M is not empty. Okay? So now we have this beautiful theorem, beautiful theorem, Baire. Okay? Let MD M be a complete metric space. Okay. Let ON be a sequence of open subsets of M. Assume that each ON is dense, then the intersection of the ONs is dense. The proof is technical. We're going to just give some ideas of the proof. Idea of the proof. So let X be in M and epsilon positive. We need to prove that the intersection of the ONs intersect with the ball is not empty. Okay, since O1 is dense, then O1 intersect the open ball is not empty. This is the intersection of two open sets, therefore it is open. Okay, so let x1 belongs to this intersection, then there exists epsilon 1 less than epsilon over 2 such that the open ball is in O1 intersects the open ball. So by induction, there exists a sequence xn of points of M and a sequence epsilon n of positive numbers such that number 1, epsilon n plus 1 is less than epsilon n over 2, and number 2, the open ball is included in ON plus 1 intersect the open ball xn epsilon n. Good. Clearly, for any n, for all n greater than 1, clearly we have epsilon n less than epsilon over 2 to the power n. Okay? For all n greater than 1. And for any m greater than n, we have the open ball xm epsilon m is in the open ball xn epsilon n. In particular, the distance from xm to xn is going to be less than epsilon n, which implies that the sequence xn is Cauchy. And this is the step where we need the completeness of M. Since M is complete, limit of xn equal to z exists in M. Okay, now number one, using this property, we get the distance from z to xn is less or equal than epsilon n less than 2 epsilon n. Okay? So z belongs to the open ball xn plus 1 to epsilon n plus 1, which is included in the open ball xn epsilon n. Once we have that, okay, we notice that because of, since the open ball is in ON intersect the open ball x epsilon, then Z belongs to the open set ON intersect. Therefore, so Z belongs to the intersection of the ONs intersect which implies that the intersection is not empty, which is the desired result of the theorem that we just announced, or the Baire theorem. Next, before we state, so the proof is complete, and next we look at another equivalent statement, or corollary if you want, but in order for us to look at that one, we need the following property to connect dense with another property. So recall an easy fact, the following, that let A subset of M, A interior, okay, is empty if and only if the complement is dense. It's very easy to prove. So to be dense is equivalent to have its complement has an empty interior. And as a corollary, we get the following result to the Baire theorem. Let MD and be a complete metric space. Let AN be a sequence of subsets in M such that M is the union of the ANs. Then there exists one of them such that AN0 has a non-empty interior. This is a very powerful theorem interior, meaning that AN0 interior is not empty. It's a very powerful theorem, and we'll see some major applications of it when we deal with Banach spaces and normal normed vector spaces. Thank you very much for your attention, and good luck.